Lecture 33. So today we're going to talk about quadratic forms and the application of, so this is another application, of the spectral theorem to quadratic forms. So what is a quadratic form? So this is quite general. So let V be a vector space over a field F. And we're going to assume that the characteristic of the field is not equal to 2. So remember what that means. That means that 1 plus 1 is not equal to 0. In other words, right, the element in the field, which is called the element 1 plus 1 is called 2. And so 2 is not equal to 0. And if 2 is not equal to 0, there's an inverse of 2. So 2 has an inverse. So in other words, this means that we have an element 1/2 in F. We're going to use that in a second. So let beta from V cross V to F be a symmetric bilinear form right? So for every pair, so for all VW in the vector space, we have that beta of VW is in the ground field, right? And it's linear in each argument, and it's symmetric, means this property. And that's the symmetry. And so now I define the associated quadratic form So for every symmetric bilinear form, I have an associated quadratic form, and it's defined like this. So Q is just a function from the vector space to the field, not from pairs of vectors to F, but only from one vector to F. And how is this defined? Well, V is defined, the image of V is Q of V, and Q of V is simply beta of V, and with this is beta of V with itself. So, for example, if F is the real numbers, F is the real numbers, and beta is an inner product, Euclidean inner product. Right, such a thing is bilinear and it's symmetric. It's also positive definite, but we're not interested in the positive definiteness right now. It's just an example of an inner product. Sorry, an example of a symmetric bilinear form on a vector space. Then, right, this associated quadratic form is defined by Q of V, well, is as the inner product of V with itself, and that's the same thing as the length of V squared. So in the case of an inner product, the associated quadratic form is the length squared. That's just an example. So we turn the bilinear form, which has two arguments, into a function of one argument simply by repeating the argument. And that's the associated quadratic form. I guess we should do some, maybe just a concrete example. So, right, so if the vector space is f to the n, then so every symmetric bilinear form is given by a matrix. Right, so right, remember, if I have a bilinear form, so if beta from Fn cross Fn to F is bilinear, then the matrix of the bilinear form, of course, if we're in Fn, we use the standard basis. So the matrix of the bilinear form is the matrix which collects all the beta of right. So by this notation, I mean, right, the big parentheses denotes a matrix, and ij are the row index and the column index. And so for every pair of indices, row and column index, here is the matrix entry beta of Eij. So if we have a bilinear form, the associate matrix is just given by evaluating the bilinear form on the basis vectors like this and putting them all in a matrix. We get a square matrix that way. So this is the matrix of beta. And it's a symmetric matrix, right? Because if I swap the entries Ei and j, I get the same. Okay. Okay. So and then so conversely, if A is a symmetric matrix, right? We get the corresponding form by beta of x, y, by this formula here. So if x and y are column vectors, I turn the first column vector into a row vector by taking the transpose matrix and then doing this matrix multiplication, which gives us an element in the ground field. And we had seen that, so for every bilinear form, we get an associate matrix, which is symmetric. For every symmetric matrix, we get an associated bilinear form, right? So this sets up the bijection between bilinear forms and symmetric matrices. And so just to be explicit, this is a symmetric matrix. So then, so the associated bilinear form, right, looks like this. So beta of xy is x1, x2, x3 times 1, 2, 1, 2, 4, 0, 1, 0, 3 times y1, y2, y3. And then you can multiply all this out and you get, so x1, y1 plus, so there's a x1, so it's 4, x1, y2 plus 2, x1, y3 plus 4, y1, oops. Let me do this again. Let me do this in 2 steps. So evaluate this matrix on this vector, gives us the linear combination. So y1 multiplies the first column, y1, 2, y1, y1, 2, y2, 4, y2, 0, and y3, 0, 3, y3. Sorry. So I'm supposed to take, when I apply this matrix to the vector, I take the linear combination y1 times the first vector plus y2 times the second vector plus y3 times the third vector. And now I have this row vector times the column vector, which is a dot product. So this is now x1, y1 plus 2x1, y2 plus x1, y3 plus, now it's x2 times 2y1 plus 4x2, y2 plus 0, and then it's x3, y1 plus 0 plus 3x3, y3. Which is equal to, yeah, no, sorry, that's just the way it is. Let's leave it at that. So now let's compute the associated quadratic form. So Q of x, which is Q of x1, x2, x3, right? This is beta of x1, x2, x3, and x1, x2, x3. So we get it from the previous formula by setting all the y's equal to the x's. And so I just plug in for y1 and y2, y3, x1, x2, x3. And so I get x1 squared plus, you see, now the x1, y2 turns into x1, y2, sorry, x1, x2, and x2, y1 turns into x2, x1. So both of these terms turn into x1, x2. So altogether we have 4 x1, x2. These two terms combine. Similarly, x1, y3 and x3, y1 combine to x1, y, x1, x3. So we have plus 2 x1, x3. These two terms combine to 0. So let's say 0 times x1, x2, so x2, x3, plus, then this, there's a 4 x2 squared and a 3 x3 squared. So this, so every term is quadratic in the components of the vector x1, x2, x3. And so all of these terms are quadratic. There's x1 squared, x2 squared, x3 squared. Those are the 3 square terms. And then there's the these other terms, x1, x2, x1, x3, and x2, x3. So altogether, if the quadratic form has 3 arguments, x1, x2, x3, there's altogether 6 terms here. Right? Even though the matrix of the bilinear form has 9 terms in it, it's a square matrix, 3 by 3, there's 9 terms, but because it's symmetric, these 2 entries are equal, these 2 are equal, and those 2 are equal, so there's 6. Okay. So, right, and as you note, so the coefficients in front of x1 squared, x2 squared, and x3 squared, those are the diagonal terms of this matrix. And these other terms here, these off-diagonal terms, each one is the sum of the two of these two terms. So this 4 was 2 plus 2, this 2 was 1 plus 1, and that 0 was 0 plus 0. And so conversely, well, so let me write something. So let me do in general. So if A is the matrix of the bilinear form beta, then so Q, the associated quadratic form of x1 through xn, well, this is given as x1 through xn as a row vector times the matrix A times x1 through xn as a column vector. And this is the sum over all I and j, xi, ai, j, xj. And we can rewrite this as the sum. So where the index is equal, so we have ai xi squared, and then the terms where the indices are not equal. So let's write this I less than j, and then we have so we have xi aij xj plus, but if we only sum, well, okay, let me then write this like this, and I greater than j, xi, aij, xj. So I've just split up the sum into the three parts where I is equal to j, and I've written this like this. And here's I less than j and I bigger than j. But if I, this sum here, if I just change the roles of I and j, so relabel I, call I j and j I, then this is a sum. So if wherever I write I write j. So instead of I write j, a, j, I, x, I. You see, now this term here is the same as this term here. I less than j, I less than j, xi, aij, xj, xi, a, ji, xj, but since a is symmetric, aji is equal to iaj. So this is in fact twice. So let me write this again. So the quadratic form has this form. So we've now seen in complete generality that the quadratic form is quadratic in these elements x1 through xn. There's the terms, the x1 squared through xn squared, they're here, and in front of them you have the diagonal entries of the matrix, and then here the cross terms xi times xj, and the coefficient in front of xi xj is right, twice aij, right, which is also so. So therefore, so you can also, to get from Q to the matrix A, right? To simply write Q like this: Q x1 through xn. Like, there's going to be these terms plus, let's say, bij xi xj. Then to get the AI, so aii, these ai and aij is equal to 1/2 bij, and aji is 1/2 bij. This is the general formula. So so back to an example. Right, if my quadratic form x1, x2, x3 looks like this, x1 squared plus 4x2 squared plus 3x3 squared plus 4x1, x2 plus 2x1, x3, then the corresponding matrix, I have 1, 4, and 3 along the diagonal. And then I have the x1, x2 term has 2 in front, so that corresponds to these 2. And x1, x3 has a 2 in front, and I distribute the 2 equally like that. And then there's no x2, x3 term, so this corresponds to 0. Right, so if I have the quadratic form written out as formulas, I can reconstruct the matrix, and therefore also beta. Okay, so this is so the relation between quadratic forms and bilinear forms. Where am I? Oh. Let me just remark, so let's go back to the general case. So remember, at the beginning, I had started with a symmetric bilinear form and defined the associated quadratic form by this formula. And to remark, so the symmetric bilinear form beta can be reconstructed from Q by the formula that beta of VW is equal to 1/2 Q of V plus W minus Q of V minus Q of W. And you just, this is just an equation you can check, right? Just simply check that if you have a bilinear form, then yeah, and the Q is the associated quadratic form. So this is beta of V plus W, V plus W. And this is beta of VV and beta of WW. So this is a true formula for every symmetric bilinear form. This formula beta of VW is equal to 1/2 of this expression. You can easily check this, just multiply this expression out, right? You have beta of V and V, which cancels this term. You have beta of W and W, which cancels this term. And then you have the cross terms, beta of VW and beta WV, which are both equal because beta symmetric and give you that term there. And so you see, to reconstruct the bilinear form from the quadratic form, we need this inverse of 2. We need 1/2 to be in the field. So if the characteristic of the field is not equal to 2, we have a 1-to-1 correspondence between quadratic forms. Well, I should say between bilinear forms, symmetric bilinear forms, and their associated quadratic forms. So I just to recall, I had explained that first in the example that if we have the quadratic form, here, Q of x1, x2, x3 given like this, then we can reconstruct the matrix it came for. Right. Anyway, so let's move on. So now, so I have to now let's go back to considering a Euclidean vector space. So now let V with an inner product be a Euclidean vector space. So given a self-adjoint endomorphism F from V to V, right? Recall that that means that VFW is FVW. Given a self-adjoint endomorphism, we can define a corresponding symmetric bilinear form beta associated to F by the formula beta of VW is equal to VFW. Well, I mean, it's clear that this is linear in each argument. For example, if I want to, in the first argument of beta is the same as the first argument of v, and so then since the inner product is linear in the first argument, beta is linear in the first argument. The second argument of beta is given as the composition of the linear map F with the second argument of the bilinear form, and so the composition of those two linear maps will be linear. So this is clearly bilinear, but also it's symmetric. Well, let's check. Beta of VW is equal to V F of W. I can move the F over to the other side. This is because F is self-adjoint. And then I can use the fact that the inner product is symmetric to rewrite this as WF of V. And then by definition, WF of V is beta of WV. This is the definition of beta. And so indeed, we have that beta is symmetric. So if we have a self-adjoint endomorphism, we get a corresponding symmetric bilinear form like this. And conversely, for every bilinear form, beta there exists a unique self-adjoint endomorphism F from B to V such that beta is this associated symmetric bilinear form to F. So beta of VW is inner product of V F of W for all VW and V. So I should probably just prove this converse statement. Let's just prove that. So for the proof, it's convenient to let's choose an orthonormal basis. So so let A, let's say let A be the matrix. So right, for the statement I have given a bilinear form. So so I should set this, let beta be given. And then we choose the orthonormal basis and let A be the matrix of the bilinear form with respect to this basis. Right, so the Aij coefficient is beta of Ui Uj. Right, the matrix of a bilinear form is just obtained by evaluating the bilinear form on the matrix vectors, on the basis vectors. Then let F be the endomorphism whose matrix, such that the matrix of F with respect to this basis B, well, this basis U1 through UN is equal to A. Right, so we start with our bilinear form. The bilinear form has a matrix, which is A, and then I just define the endomorphism given by that matrix A to be F. Right? Once I have a basis, there's a one-to-one correspondence between the matrices and the linear maps. So once I have a matrix, I just define the corresponding linear map. Then remember, this is an orthonormal basis, and so the matrix elements of the linear map F are given by right, so these matrix elements Aij are then going to be Ui F of Uj. Right, we had discussed that for an orthonormal basis, the matrix elements of a linear transformation can just be computed like this, or of an endomorphism, I should say. Right, so so right, and remember that right, since this is an orthonormal basis, when we set up the correspondence between so an orthonormal basis, so a endomorphism is self-adjoint if and only if the matrix is symmetric, right? So then F is self-adjoint because A is symmetric. And A is symmetric because beta was given as a symmetric bilinear form. So, so F is an endomorphism, which is self-adjoint. And so now I have to prove my formula that, so let me just compute. So, right, my claim is, so now I've produced an endomorphism. My claim is that the associated bilinear form, which is given by this formula, is the one I started out with, namely beta. So let's just compute. Well, if I take arbitrary vectors v and w, I can express them in terms of my orthonormal basis. Right, v is some coefficients vi times ui, and then there's f, and here's j, wj, ui. By the bilinearity of the inner product, this is the same as I and j. Ei, wj, I can take the scalars out front and then have ui, f, uj. But these ui, f, uj, right, this is equal to aij, but aij is beta ui, uj. So this is summation ij, vi, wj, beta of ui, uj. And then I use the bilinearity of beta to move the vi and the wj back inside, and I get beta summation I, vi, ui, summation j, wj, uj. And this was v, and that was w. So indeed, the associated quadratic form to the self-adjoint operator I had produced is the beta I started out with. So, so just recall, what had we just seen? So V, this is the Euclidean vector space, U1 through UN, an orthonormal basis then we have symmetric bilinear forms on V. We have the self-adjoint endomorphisms of V, and we have the symmetric matrices. Then all these sets correspond to each other, one-to-one. But for every symmetric bilinear form, I had started out by saying if I have a self-adjoint endomorphism, I define a corresponding symmetric bilinear form. And then I had proved that for every bilinear form, I get a corresponding self-adjoint endomorphism. But in the proof, I had used an orthonormal basis, and I'd actually seen that that both the symmetric bilinear forms and the self-adjoint endomorphisms correspond to symmetric matrices. So in the Euclidean vector space with an orthonormal basis, all these three concepts actually turn out to be completely equivalent to each other. And right, since the real numbers are of characteristic 2, this is also one-to-one correspondence between two quadratic forms. Okay, so now so because we had proved the spectral theorem, and it was about self-adjoint endomorphisms, and proved something about self-adjoint endomorphisms, we can now translate into a statement about symmetric bilinear forms, and therefore a statement about quadratic forms. So the spectral theorem says that for every quadratic form, Q from V to R, there exists an orthonormal basis of V such that I'm sorry, such that well, and so if I write Q of a vector, so now I'm going to express Q, I express the vector V in terms of the orthonormal basis. So where and so So diagonalizing the self-adjoint endomorphism is equivalent to diagonalizing this symmetric matrix. And if I've diagonalized the symmetric matrix of the bilinear form, that means the bilinear form has no off-diagonal terms. So the bilinear forms, that, in this expression of the quadratic form, there's no cross terms. We've eliminated the cross terms. So there exists an orthonormal basis, so without cross terms. That's the important thing. And and the coefficients in front are, of course, the eigenvalues of the associated endomorphism or matrix. So let me do an example. Let's see how this works in action. So so this is an example in R2. And we consider a quadratic form Q of xy 11 over 4 x squared minus 1/2 square root 3xy plus 9 over 4 y squared. And we can also, as this defines, that's what defines some kind of curve in R2 by setting qxy equals 1. So this is the curve 11 over 4x squared minus 1/2 square root 3xy plus 9 over 4y squared is equal to 1. And in fact, it's going to be some kind of conic section. So all the points xy that satisfy this equation. So, so you might start out with this kind of equation. You write down the corresponding quadratic form, the corresponding matrix, which we discussed at the beginning, is going to have, so the term for x squared is 11 over 4, the term for y squared is 9 over 4, and the cross term gets distributed equally. So we need minus 1 over 4 square root 3 and minus 1 over 4 square root of 3. That's the corresponding matrix, symmetric matrix. And that symmetric matrix defines a bilinear form, and it defines a self-adjoint endomorphism, and it defines the quadratic form. And so let's diagonalize this matrix A. So, excuse me. Yeah, I might go 10 minutes over. I'm sorry. If you have to go, I won't hold it against you. You can watch the rest of it later. But I want to finish this example, so I'm just going to finish this now. So diagonalize A. So let's find the characteristic polynomial, 11 over 4 minus lambda minus a quarter square root 3, 9 over 4 minus lambda. So 11 over 4 minus lambda times 9 over 4 minus lambda. Minus 1 over 16 times 3. That is the determinant of this matrix. This times this minus that. Yeah. So here we have a lambda squared term. Then we have minus 11, 4, minus 11 over 4, minus 9 over 4 is minus 20 over 4, which is minus 5 lambda. And then it is plus 99 over 16. That is obviously supposed to come out with nicer numbers. Where is 11, 9? Is there a negative? What am I doing wrong again? Lambda squared minus 5 lambda. I think there's a negative. Where's the negative? Oh. Oh well. It's just like my calculation skills are poor because 96 divided by 16 is actually 6. No, I think I did it all correctly here now. So here's here's my quadratic form. 11 over 4 goes there, 9 over 4 goes there, and minus a half square root of 3 turns into these two terms here. I've got this characteristic polynomial. So this is lambda minus 2 times lambda minus 3. So there's lambda equals 2. Lambda equals 3 are the eigenvalues. So let me compute the eigenspaces. So lambda equals 2 gives me 11 over 4 minus 2 minus 1 over 4 squared of 3 minus 1 over 4 squared of 3 and 9 over 4 minus 2. So 2 is the same as 8 over 4. So this is 3 over 4. This is minus So 9 over 4 minus 8 over 4 is 1 over 4. So let's get rid of some denominators. So the null space of this matrix is spanned by by 1 squared of 3. Sorry, the sun is coming in and messing up. Okay. Null space is spanned by the vector 1 squared of 3, because if I right, 3 minus square root of 3 times square root of 3 is 0, and minus square root of 3 times 1 plus square root of 3 is 0. So that is the null space spanned by this. So this is an eigenvector, and then for lambda equals 3, the other one. So we have 11 over 4 minus 3. And then 9 over 4 minus 3. So this time this matrix is, so 11 minus 12 is minus 1 over 4. And this is 9 minus 12 is minus 3 over 4. And so the null space is spanned by say 1 and square root of minus square root of 3. No. Yes. So so my change of basis matrix P, which has the eigenvectors on the diagonal, eigenvectors on the diagonal. So the first eigenvector was 1 root 3. The second eigenvector was root 3 minus 1. Oh, by the way, so notice that my two eigenvectors, so V1 is 1 root 3. That one was the first one. The second one was V2 is equal to root 3 minus 1. First of all, note that they're perpendicular to each other. Right, if I take the dot product, I get root 3 minus root 3 is 0. So they're perpendicular to each other, as they should be, because they're eigenvectors of a symmetric matrix. But we want to have an orthonormal basis of eigenvectors, so we have to normalize them. So what is the length of V1? Well, it's a square root of 1 plus square root of 3 squared. So the length of V1 is square root of 4 is equal to 2. And the length of V2 is also 2. So we to normalize them, we have to divide each of them by 2. So orthonormal basis of eigenvectors. So u1 is equal to 1/2 times v1, which is 1/3. Like this is the corresponding eigenvalue 2, and then u2 is 1/2 times √3 minus 1, with the eigenvalue equals 3. So my diagonalization looks like this. Diagonalization. The matrix I started out with, 11/4, 9/4, minus √3/4, minus √3/4. Right. Here's the change of basis matrix. So which is 1/2, 1/3, √3 minus 1. Then there's the diagonal matrix, 2, 3, 0, 0. And then there's the inverse of the change of basis matrix, but now since it's an orthonormal basis, this is an orthogonal matrix, and the inverse is the transpose. And so so what has happened here? So we've changed coordinates. So we have this new orthonormal basis given by these two vectors. What does our quadratic form look like? So Q right. We know that you know, with respect to the eigenbasis, the quadratic form looks like this. Because we've gotten rid of the cross terms. Let me just say one more thing. So if we express, right, so an arbitrary vector x, y, right, so look at the coordinate vector with respect to my new basis b, right? These are the x prime and y prime coordinates. So the original coordinates are x and y. If I express the vectors in the basis b, I get the coordinates x prime, y prime. Right, remember that so x prime, y prime is given by the inverse of the change of basis matrix in terms of x, y. So in our case, x prime, y prime is equal to, there's this inverse matrix. And so if I write this out, I get x prime, sorry, but I can also write it like this, the old coordinates in terms of the new ones. this case, the matrix happens to be the same. And the point is that, so if you substitute into the original equation, which substitute this into the original equation, 11 over 4x squared minus 1/2 root 3 xy plus 9 over 4y squared is equal to 1. Substitute the relation between, so the expression of the old coordinates in terms of the new coordinates into the old equation. You get the new equation, x prime, well, 2x prime squared plus 3y prime squared is equal to 1. Anyway, so here are the x and y axes, and my first basis vector is right, so u1, where was it? So this 1/2, 1 and root 3. This is this u1. This is at a 60-degree angle. u2 is 1/2 times root 3 minus 1. So the y coordinate is minus 1/2. The x coordinate is positive, so this is so there's u2. And so so this is the new x prime axis. This is the y prime axis. And so in the new coordinates, the equation is like this. So I can rewrite this as x prime over 1 over root 2 squared plus y prime over 1 over root 3 squared is equal to 1. And so I see that this is an ellipse with the major minor axes being equal to 1 over root 2 and 1 over root 3. So 1 over root 2 is the bigger one. So that's going to be here, something like that. So there is the ellipse 2x prime squared plus 3y prime squared is equal to 1. The new coordinates, or in the old coordinates, it has this equation here. So what happened is that we started out with so this equation describes the ellipse, but it was expressed in coordinates that were not aligned with the major and minor axis of the ellipse. It turns out that the eigenspaces, the two eigenspaces that we found, are the major and the minor axis of the ellipse. So in general, so the eigenspaces of the symmetric matrix corresponding to the quadratic form are the principal axes of this hypersurface. So in the and the eigenvalues correspond to the major minor, you know, the I don't know what's the word of these, the length. So you know, 1 over this. So the reciprocal of the square roots of the eigenvalues are the major and minor axis in the case of an ellipse. So anyway, I've already talked way too much. So let me just finish here with this example. And thanks for hanging with me. Okay, that's it for today. Let me stop this.